So I think we are ready to start. So I'm going to talk about large-scale machine learning in Spark. I'm a machine learning engineer at Alpine Data Lab. My name is Tsai. So if you guys have any problem about Spark, you can find me on internet and send me email. Okay, so let's start. So basically, we are a machine learning company, and in the beginning, we are trying to solve machine learning problem for lots of enterprise customer. But the problem is that, lots of time it's hard in general, for lots of customers to find machine learning engineer to implement the algorithm by themselves and then make it scale. So we are trying to help customer to do this kind of job. And in the beginning, people use database to store the data. So we create an open source project called MapReduce, and it's a database, machine learning processing framework. And then gradually we saw lots of customers start to move to Hadoop. So they try to, try to archive the data in Hadoop and try to process it offline. Think about it like Yahoo or eBay. They have couple terabytes of data every day, and it's impossible to store them in database and process over there. So in general, they do ETL every day and dump the data to Hadoop. So we start to work with Hadoop, but we found there are lots of limitations with Hadoop. Something like, lots of machine learning algorithms are iterative. So how can Hadoop work well in this situation? Because there are lots of I/O overhead inside Hadoop when you read the data from HDFS. So we found Spark is the best platform for us to do machine learning because its in-memory caching mechanism allow us to cache the data when we see the data first time, and the second time when we iterate through the data, we just read it from memory. So that's why we put lots of resources in Spark and work closely with community and contribute our code to Spark project. So today, I'm going to talk through the basic Spark architecture, including what is transformation, what is action, the basic idea how Spark works, how to do a persistent caching inside Spark, the different type of persistent level. And then I'm going to talk about a couple algorithms as a demonstration, how to use MLlib API inside Spark. So this is what I'm going to talk about. And if you guys have any question, just stop me, and I'm willing to answer any question immediately. Okay, so in my company, we implement, let's say, logistic regression. And we found that compared with the Hadoop MapReduce solution and Spark solution, the performance speed up is like a couple hundred times difference. So I'm going to go through the detail later. Okay, so before MLlib exists or Spark exists, most of the people use Mahu to do large-scale machine learning. But the problem is that MapReduce is designed for the batch processing. So whenever you deal with the iterative algorithm like a K-Means, logistic regression, or linear regression with so many columns, so you cannot solve it exactly. You need to use some optimization process to solve it. Then MapReduce is not a good candidate to do it. And we found that lots of companies or lots of people to find a way to work around it by just subsample the data, right, and train the model with subsample of the data, and then do some kind of like ensemble average on the model. But it's in general doesn't give you really good accuracy in terms of comparing with the training with the full data set. And this is the benchmark from Spark community, so I already mentioned briefly. So let's skip this slide. Okay, so why people use MLlib? MLlib is a sub-project inside Spark. So Spark is an Apache project, and MLlib is one of the sub-projects. And it's shipped with Apache Spark since version 0.8. And we put lots of engineering design effort into MLlib project. And we have more than 50 contributors since July 2014. So the community is really active right now. We have so many pull requests every day, and we are trying to implement lots of new algorithms inside Spark. And those are the current status of the Spark. So basically, those are current algorithms we have inside MLlib. So we have SVM, logistic regression, decision tree, naive Bayes, random forest. We're gonna have it in Spark 1.2. But if you guys want to try it out, it's already in the master, so you can download it from the GitHub. And for the regression side, we have linear regression and of course using random forest to do regression. And we have collaborative filtering to do the recommendation system using AOS. So for collaborative filtering, I know a couple companies has it in production right now. And we have K-Means, we have PCA, SVD, and some basic statistic tools like summary stats, correlation, something like random data generation. And we start to work on text mining as well. So we already have TF-IDF, O2 vector, and we are going to have LDA in next release. I hope. We are working on that right now. And we have something like a StandardScaler, Normalizer for data preprocessing. Okay, so let's briefly go through the MapReduce. So MapReduce is a way that people right now, it's probably the standard way people deal with big data right now. And it's invented by Google at 2004. And it's scaled linearly, nearly, and it's considered a data locality. So basically, you push the code to the data instead of pulling the data to the machine. And it has the fault tolerance mechanism built in the data storage by replication. So inside the HDFS, you can have multiple copies of the data, and in case one machine dies, you still have the data. And also has fault tolerance in terms of computation. So basically, if one machine dies during the computation, the other machine can restart the job again. So let's go do an overview how people design algorithm in Hadoop. So inside Hadoop, there's a mapper. Mapper basically load the data and emit a key value pair. And reducer can collect all the value with the same key, and then you can do some kind of algorithm on top of it. And combiner is that a way that you can avoid shuffle phase, because when you do mapper and reducer, basically all the key value pair emitted gonna transfer to the reducer. And then you can pull different data from different machine into the other machine. So you're gonna have lots of traffic. So you want to combine those data before you do the shuffle. So basically you can do combiner in the mapper side. But the problem for combiner is that it's basically a buffer. So basically you are combining everything inside a particular buffer. So you are not actually combining everything. So lots of time, the performance is not good, and combiner is not guaranteed in Hadoop. So there's one other way people can do is called in-mapper combiner. So the way people does is that in the mapper side, you can create an LRU cache, right? So you can keep aggregating your data in the mapper side without emitting to the reducer, okay? But what if the cache is full? So you just emit it whenever the cache is full. So it's called in-mapper combiner. So it's much more efficient. And you are just emitting the least used element to the reducer. So you can keep most of the key on the mapper side. So it can actually speed up the whole process by a couple times. There is a reference, you can check it out. And from peak 0.10, they actually have it built inside the peak. Okay? So the question about Hadoop is that it has a built-in fault tolerance, its scale, it's production proven in the industry. But the problem of the Hadoop is that it's optimized for disk I/O without leveraging the memory. Think about it, when people do Hadoop, it's 2007, 2008. At that time, the memory is not as cheap as nowadays. So people actually do lots of processing from the disk I/O instead of caching it in the memory. But right now, the memory is so cheap, why don't we leverage our memory and cache some data? So that's one problem. And the other problem is that if you guys has ever implement any MapReduce application, you will see the API is so dirty. I think partially it's because of Java. And you need to set up mapper, reducer, and it's difficult to do unit testing, and everything just mess up. Even you want to pass a small variable from the driver to the map side, it's so difficult. You either need, put it in the distributed cache, and then read it in the mapper, or you just put it in the configuration. So you need to serialize it and then put it in the configuration and push it to the mapper and read it in the setup method inside the mapper. So it is so difficult to develop, and it's really easy to make some mistake. So how about Spark? Spark is actually use MapReduce as the programming model as well. So everything you learn in developing MapReduce Hadoop, MapReduce application can be applied in Spark. And with Spark spreadsheet API, basically it's written in Scala. The code can be 5 to 10 times less than the Java, compared with Java. And more importantly, it's not just a distributed computation framework. So Hadoop MapReduce is a distributed computational framework. So you need to write lots of code for your application. But in Spark, we provide lots of preview components which can help you quickly implement your own project. So we have Spark streaming. It's kind of like a stone. We have Spark SQL. So basically, you can run SQL query on top of your data set with Spark. We also support Hive query, actually, inside Spark SQL. And it's an easy way to deal with the Parquet or Evernote file format. And we have MLlib, of course, is a machine learning library inside Spark. And we have GraphX for the graph processing. So the most important concept inside Spark is RDD, a resilient distributed data set. So you can think about it as a collection of the element in parallel. So think about you have a cluster and you have a bunch of workers working, right? So whenever you load the data from HDFS or whatever, Hive, or you can even load the data from S3. When you load the data to RDD, basically you can think about it, it's loading the data on different machine, and then it's just collection of those data. So whenever driver manipulating those data, it's actually distributed in different machine, not in the driver side, not in a single machine. Okay, so it's an abstraction of the data. But when you actually manipulate it, you can use some kind of like map or reduce or full lab, this type of Scala API. It's kind of similar to Scala API. So you can manipulate it locally, but we actually push the code to the remote computation worker and execute it over there and pull it out to driver at some point if you want to see the result. And RDD is fault tolerance. So whenever one machine dies, the other machine or the other worker gonna load the data automatically. Okay, so you can think about it. You visualize the whole process like this. So when you do K-Means, right, you have input data, and then you iterate through the data a couple times. So you read the data from HDFS, and then write back the current, the updated centers, right? And you use it as the next initial condition and run the K-Means algorithm again. So you need to keep read the data from HDFS and write a small model into HDFS and load it in the next MapReduce job. Okay, so that's why it's not efficient at all. You keep reading the I/O. But with Spark, you read the data first time and cache it inside the memory. And for the next iteration, you read the data directly from the memory. And you may wonder what happens if the size of data is larger than the memory size. So in Spark, if the data is larger than memory size, we're gonna do partial cache. So we only cache partial, some part of the data, and the other we still read it from HDFS. So this still gives you some performance gain compared with MapReduce. It's just without caching in Hadoop MapReduce. So there are two types of operation on RDD, which are very important. So the first one is transformation. The second one is called action. And for transformation, we create a new data set from the existing RDD. So they are actually lazy evaluation. So when you do any transformation, they won't actually get executed or carried out immediately. You're gonna wait until you perform an action, okay? So action is actually return a value to the driver program or store the data back to HDFS. And it does make sense because when you do transformation, you don't need to know the result, right? Because you probably do map or frame map, doing some kind of transformation on top of your RDD of data. And you don't need the result immediately. But you only need the result when you do an action, because when you do action, you are actually pulling the data to the driver or saving the data into HDFS. This is the only time you need to do the whole computation. And this kind of lazy evaluation mechanism actually allows Spark to do more sophisticated job in terms of the optimization. Because you can do bunch of transformation on top of one RDD. You can do one RDD, the map, and for each element, you multiply by 2, right? And you do train another map operation. You can do another map operation by something like, doing the square or something like that. And because of lazy evaluation, we are able to combine all those transformations together and execute it at the same time. So that's why Spark has a really good performance, one of the reasons. So I'm going to quickly go through the API, transformation API. We have a map. So basically, you are taking a function which can take an input and create a new output. And filter, so we can have some condition from the input. And then we only return those elements which satisfy the condition. We have frame map. So the difference between map and frame map is that for map, for each input, you create an output. But frame map, for each input, you can create multiple output or none of the output. Okay, you have map partition. So map partition is kind of similar to Hadoop MapReduce mapper. So you can have a full construction on the whole partition, and then you can do some local variable over there, and it's sometimes more efficient. And you can do group by key. It's kind of like a Hadoop reducer. So basically, you group all the key value pair with the same key, and then you get an iterator. So you can iterate through the load value. And you have reduce by key. And reduce by key in general is more efficient than group by key. So reduce by key you can carry out the reduce in the map side. So it's much more efficient. Okay, and for action, you have reduce. So basically, for the action, you aggregate those elements from the RDD, and then you return the data back to the driver. And you have collect meaning that pulling all the data from RDD to the driver. So it's really dangerous sometimes because you can potentially, let's say your whole cluster has 10 terabytes of data. And if you mistakenly do collect, you are going to pull all the data into a single machine and the whole cluster is gonna crash. So it's really dangerous. And you have count how many data you have, and you have take the first element, take the first n element. You can save the data as text file into HDFS. So those are the actions. So only when you execute action, the whole computation won't be started. And RDD has different persistent or cache mechanism, as we talked about. So you can cache the data in the memory, but there are a couple ways you can do. Okay, so for the storage level, you can have memory only, or memory and disk, or memory and serialization, memory and disk serialization. So the difference is that memory only is that when you try to cache the data, you are trying to cache the data in the memory. However, if the the intermediate RDD has bigger size than memory, you don't cache it. So you read it from the disk. But for memory and disk is that whenever the data is larger than memory, you cache the data which cannot be cached in the memory on the local file system. So what's the difference between memory only and memory and disk? Because it seems that for those data which cannot be cached, we always read it from disk, right? So the difference is that imagine that you have a job, a really expensive RDD, which is created by previous RDD. You do a transformation, right? And then you want to recycle it again. You want to use it later on for different purpose, okay? And this transformation is really expensive. So if you do memory only, you cache the data in the memory. But those data which cannot be cached in the memory gonna be recalculated. So the whole transformation process gonna be recarried again. So it's gonna recompute again for the transformation part. If this RDD is derived from the other RDD, okay? And if memory and disk, okay, for the data which cannot be cached in the memory, it's gonna directly have a full copy in the local disk. And the good thing is that you don't need to recompute again the transformation, which can be really expensive. And you can have a serialization in a caching when you do caching. And the difference is that when you do a serialization, it means you actually serialize the data in Java, and then you can do compression. You can use zip or snappy to compress the data. So turn out to be, in general, the data gonna be smaller, about 40–50% of the original data, but you are trading some computational time by doing that, because you need to decompress it, you need to compress it and cache it. But in general, I recommend to do compression, because lots of time, it depends on your data set. Lots of time you can get really small data compared with caching the data in the original format. Okay, so this is an example how we do workout in Spark. I have typo, it's actually Spark. So you read the data, Spark test file, you read the data, you do a frame map, and then for each line of the data, you split it by space. And for each word, you create a tuple called word and one, and then you reduce by key. Okay? So in this case, you can do a word count. How simple is it? I mean, compared with the Hadoop MapReduce. Okay? So this code can be optimized either using a mapper combiner or using a local, hash map with map partition. But this is another story. Okay, and let's talk about something else. So how about we want to compute? You load the data, which is text file. It has a bunch of number. So each line of the data is a number, okay? And you want to compute the mean of the number. How can we do it inside Spark? So what you can do is that you can read the data by using the Spark API text file. You get the input data, okay? You cache it by getting a cache RDD, okay? And then you can do cache RDD.map. For each line, you create a tuple, right? And it's gonna be a value and one, okay? And reduce is reducing those tuple, okay? So you can visualize it by the diagram, okay? So you have a two executor right now. Okay, so for 3.2, in the first executor, you create a tuple called 3.1, 2.1, and the reduce function inside Spark is complete. So basically, you're gonna apply it in the mapper side first. So you're gonna apply it in mapper side, and then using the same reduce function to reduce the between different executor. So that's why you get 5.2 and 6.2, okay? And then you reduce it again from different JVM. So executor 1 has its own JVM, executor 2 has its own JVM, okay? But the downside for doing this is that you have lots of garbage collection, right? Because for each input, like 3.0, okay, you create a tuple first, and you apply reduce. So you kill the first object. So basically, you have lots of garbage collection, GC overhead over there. So we have better way to do it. let's talk about that. So you can, another API called MapPartition, you can actually use it to do a better job. So MapPartition basically is that taking a function which gonna have input of iterator and output of the another iterator. So how can we do it, okay? So we are doing similar thing. But we can have, in both of the executor, we can have the global variable, but it's only global in the executor. So let's say we have count and sum over there. And then you can, because you have iterator in each partition, right? And the data is small enough for each partition. So basically you have iterator loop through the data, okay? So you can accumulate them in the JVM without creating a new object. So you are just keeping adding the sum and keeping adding the count. And then it means the final result, 5-2. So it's much more efficient. Okay, so basically lots of time you can use MapPartition to get better performance. Okay, so let's go back to talk about MLlib, because we have a basic introduction to Spark, and we want to focus on machine learning. So the way we design API inside MLlib is that we try to make it work well with Spark code system and Spark SQL right now. So basically people can use the basic building block, something like load transformation or action, to do the data preprocessing, to do the data cleaning up. Because lots of time, machine learning engineer or data scientists spend lots of time on cleaning up the data, right? Try to find out feature you need. So you can use Spark SQL. Basically, you are just using Hive or SQL query to clean up the data. Everyone in computer science knows how to do it. And most of the algorithms are implemented in Scala. But we have most of the public interface. We don't use the advanced Scala feature. So the Java user can directly call those API. And we also have Python bounding, many of them, not all of them. So basically, the way we do is that we implement the Scala algorithm and then see if anyone in the community have time to help to write the Python bounding. But many of them actually have. And we are actually under really active development right now. So we have a bunch of API we can market. We market as experiment or develop API. So those API, we don't guarantee the compatibility between different versions. And if we actually change the API, we're going to provide a migration guide for user to easily migrate their application. But we have a really strong rule that if even we want to change the API mark as experimental, we need to have the committee review it and then approve to change the signature. So it's pretty stable actually. Okay, the code is well tested. We have lots of unit tests, and we have lots of common inside the source code. Okay, so let's talk about the data type inside the MLlib. MLlib has its own local vectors, so it's not distributed fashion or local matrix, and it's actually wrapping around Breeze implementation. So Breeze is a linear algebra package implemented in Scala. So it can do matrix multiplication, dot product of two vectors, or sum of the vector, this type of stuff. So we actually use Breeze in the background as the linear algebra package. But the problem is that the way we can convert MLlib to Breeze vector is actually private. So if you actually want to implement your algorithm, it can be a problem because you cannot access those API in MLlib. So one of the workarounds, because I'm doing lots of development using MLlib API with our company product. So what you can do is that you can have loads of code, make it as org.apache.spark MLlib scope, and then you can use those private API. But the reason why we want to do that is that we don't want to, tie into Breeze. So we don't want, make it as a public API, so people heavily use it, and at some point we want to migrate, and there's no way we can do it. So we just make it as a private. And we have all the training sample in the supervised learning. We store in LabeledPoint, which contain a label and also feature vector. And the label is the response in supervised learning. And we have distributed row matrix. So basically, it's RDD of vector, and RDD doesn't care about ordering. So it doesn't have meaning in terms of the row indexes. But we have a distributed index row matrix. So basically, what you store is RDD of a tuple, and the tuple is index and the vector. Okay, so let's talk about what's local vector. So you can in MLlib, you can actually construct a vector by doing that. Okay, so first of all, you want to construct a dense vector. So you can do dense vector, dv equal to vectors.dense, and put all the elements in a dense vector. Okay, and you can also construct sparse vector by two ways. One way is that you can construct it by given the dimension of your vector, and also key value pair. Key is the index, value is the corresponding value for that particular index. So you can do it in this way. Or, So the second way you do is that you have the first argument is how big is your dimension of the sparse vector, and the second one is the non-zero element. What is the index of the non-zero element? And the third one is the corresponding value. So this is the second way we can construct a sparse vector. And the third way is that you can have a sequence of the key value pair. Key is the non-zero value, the index of a non-zero value, and value is the corresponding value. So there are three ways you can construct a sparse vector. And as I mentioned, okay, there's some tip or trick you can do related to local vector, because sometimes in a Spark MLlib vector API, we don't provide some linear algebra implementation. So the only way you can do is that if you want to sum two vector, okay, the only way you can do is that you want to convert it into the Breeze vector and use the Breeze API to do it. And this is how we do it. So you need to put a hosting in the Spark MLlib package. And then you can access two Breeze API. So you can create a Breeze vector, and then you can do sum of the two vector or do the dot product. And also you can create sparse vector, MLlib vector from the Breeze vector. So actually converting between MLlib vector and Breeze vector, there's no big overhead, because we are actually passing the reference. Okay, so in the MLlib vector, we have a reference to the Breeze vector. So we are just returning the reference. So there's no overhead over here. And in the real code, we actually use it a lot. So it's a snapshot in the unlike Normalizer inside MLlib project. So we actually convert the MLlib vector to Breeze vector, because it allows you to use more rich API. Because Breeze has lots of rich API. For example, like a sparse vector, right? You can have active iterator. So you only iterate through the non-zero element. So in this case, even you have really big vector, but you only have 4 or 5 are non-zero, you only loop through all of them. So this is one of the good API in a Breeze. So this is the only way we can use it. Okay, and the next is LabeledPoint. So LabeledPoint is actually a class which can store, is a case class which can store the response and the training feature. Okay, so the training feature can be dense or sparse. It can be in a dense representation or sparse representation. And by doing that, it's good for us to design the algorithm, because we can design one algorithm which can train the data in dense vector or sparse vector, although we need to do some careful implementation in the algorithm, but it allows us to do that really easily. For example, our logistic regression can train the data with couple millions of features. And this is really important because in lots of natural language processing application, the feature space can be couple million, can be really large, right? But you don't want to implement an algorithm for dense vector or sparse vector separately. So you want to have a layer of abstraction. Although sometimes we cannot have really good abstraction, so in the algorithm, we actually branch out, seeing that, oh, we do pattern matching. If it's dense vector, we do something. If it's sparse vector, we do something else. But in terms of the user point of view, it's a good abstraction because they can use this as an API to train either dense or sparse data set. Okay, so let's go through the supervised learning in detail. So we have linear support vector machine. It's actually implemented using SGD. We have logistic regression. It has two versions. One is LBFGS, one is SGD. So LBFGS actually converges faster compared with the SGD. We have decision tree, random forest. It's going to be in Spark 1.2, as I talked about, and naive Bayes. And we have multi-class classification, like decision tree, naive Bayes, and also multinomial logistic regression. This is something I'm working on right now. So it's probably going to be in Spark in 1.2 or 1.3. And for regression, we have linear regression with L1, L2. And for L1, we do SGD plus soft ratio. And we have decision tree for regression, random forest for regression. Okay, so currently, okay, the regularization in the linear model in Spark has some problem. So it's penalized everything, including the intercept. So we are not able to exclude intercept from the penalization. And this is not ideal for lots of use cases. So we are actually implementing GeoMNet inside Spark. We have one implementation in my company, and it's working really great. We use OWLQN, which is a variant of the LBFGS, but OWLQN can deal with the L1 regularization because L1 is really difficult because L1 is not differentiable as the orange, and then you cannot apply LBFGS to approximate the Hessian. So you need to do OWLQN. And we have an implementation which can reproduce our GeoMNet result, so you can do hybrid, L1 plus L2, like ElasticNet right now. And we are trying to make it open source in Apache Spark. So probably gonna be in next release. Okay, so let's talk about training API. So this linear regression with SGD, stochastic gradient descent. So you load the data, you parse it, you load it as a text file over here, and you parse it. So the data is text file, and you can do map. Okay, for each line, you parse the data and create a label point, return a label point. Okay, and as I told you, map is transformation. You don't actually run it over here. You actually run it when you actually do the action later on. And then you can train the model by doing model equal to linear regression with HGD dot train and give it a, pass in the data and also the number of iteration you want. Okay, so the API is pretty simple and it's scaled up to couple terabyte of data. And we have support vector machine with SGD. It's actually binary classification. We also support loading the data from the zip SVM format. So you can actually have your data in zip SVM, pure text file, and load it into the RDD of LabeledPoint. So you split it by training set and test set, and then you can train it with SVM with SGD. Okay, so this is a new feature actually implemented by us. It's logistic regression with LBFGS. So I'm going to talk about LBFGS in the other talk in this afternoon. And essentially, it's a quasi-Newton method which converges faster than SGD. And in this API, we can train the model using LBFGS instead of SGD. It's good because user doesn't have to construct the objective function by themselves. And we also do some kind of like condition number improving on the other story. So the convergence rate can be improved. So I'm going to talk about that as well. So you can actually improve the convergence rate by standardize the training feature. And this is what Scikit and also GLMNet package do. But whenever you standardize the feature, the training feature, you make it as zero mean and union variance. Okay. Whenever you standardize it, your model will be changes, right? Because the model gonna be changed in the new space. But you can actually transfer it back to the original space without the standardization. So it's actually gonna be transparent for the user. But in terms of the optimization process, it's gonna improve a lot. And the reason why it's gonna improve a lot is that, think about it, in one case, okay? You have two-dimensional problem. You want to optimize it and find the minimal point in a two-dimensional space, okay? And in one dimension, the variance is really large. And in the other dimension, the variance is really small. So you can think about it. It's kind of like, the optimization is finding out the optimal point in this kind of, space. So you're gonna try to optimize it in a direction that has a smaller, variance. And then you find out the optimal point and then optimize it in the other direction, which has larger variance. But it's not good because in this case, you're gonna have more iteration to get it converged. And it's gonna be really slow. And sometimes for high dimensional problem, the whole optimization cannot be converged as well. So you want to standardize the training data, actually. And this is a new feature in Spark 1.1, which just released. And we only enable it in the logistic regression. Okay, so the API is also pretty simple. You can create a channel, logistic regression with LabeledPoint. You can set the convergence tolerance. So whenever you hit a convergence tolerance, you just stop the training. You can set a max number of iteration. You can set if you want add intercept or not. And then you just do the logistic regression .run and put a training RDD. That's it. So it's pretty simple. And here's the benchmark comparing the LabeledGS and gradient descent. So the first data set has 123 features, which is not too large actually. And we have 11 millions of the raw data point. And you can see LabeledGS converge faster than gradient descent. So the y edges is actually the log likelihood of the optimization process. Okay, and for RCV1 dataset, we have how many features? 67,000 features. I cannot read it, and which is 0.15 non-zero element. So it's pretty sparse. Okay, and we train it with the LabeledGS and gradient descent, and you can see gradient descent doesn't converge at all, and LabeledGS converge quite well. And this is another data set which has 1.3 million features actually, and it's 0.034% of the non-zero element. And you can see, SGD doesn't work at all as well. Okay, so this is all about logistic regression. Okay, and we also have distributed K-means. So you also load the data from the text file, okay? And you can do data.map. You try to parse the data, and the input for the K-mean is just a RDD or vector, okay? And then you can define how many number of cluster you want to find, and you also define the number of iteration. And you can just do K-mean.train and pass in the training data set and also the number of cluster and number of iteration, and you're gonna get all the cluster. So the API is pretty easy to use. like Python. We want to design it such that people who are familiar with the Python scikit can use Spark to do it in a distributed training. And we also can do PCA plus K-means. So you can have a point, which is RDD of vector. We can construct a matrix, and then we can compute PCA, and we apply the PCA, transform into the lower dimension space, and we can run K-means later on. So it's pretty useful skill, technique people use. We also have collaborative filtering for the recommendation. So basically it's ALS. So you can check out the API. It's not too difficult. We are running out of time, so I'm going to speed up. Okay, and we're going to talk about LBFGS optimization. So it's not actually a blender. It's actually a complex optimization package. So we built it and we merged it in Spark 1.0. And it's one of the popular algorithms for the parameter estimation in machine learning. And you can use it for linear regression, logistic regression, all kind of optimization problem, complex optimization problem, as long as your objective function is differentiable. Okay, so if your objective function is differentiable, the standard way people do is LBFGS, one of the standard way. Because if you use Newton method, you need to compute Hessian matrix. And the Hessian matrix has dimension square of the number of the feature you have, so it doesn't scale at all if you do Newton method. Okay, so it's not scale. Okay. And right now we are building OWQN inside Spark to deal with the L1, like lasso regression, this type of problem. It's a building block of GeoMNet, actually. Okay, so this is how we use LBFGS API. So you can define the objective function here. For example, the objective function over here is logistic gradient. So it's the gradient of the logistic function. Okay, so you can optimize it by LBFGS.run LBFGS. And then you can basically channel logistic regression. Okay, so the difference between this one and the one we have in terms of the logistic regression with LBFGS is that we also deal with the condition number improving. So before you do the training, we actually standardize the training set to make it converge faster. Okay, and we are working on weighted regularization, and this is a way that we can exclude the intercept, so the intercept will not be penalized. And we also can use it to handle the L1 regularization and smooth, regularization, which is L2, L3, or whatever, which can be differentiable. Okay, and we also work on multinomial logistic regression inside Spark. It's probably gonna be there soon. Okay, and we have transformer, so it's not this transformer. So it's a new API in Spark 1.1. So the idea is that we want to build a transformation or a pipeline like a scikit. So in scikit, you can prepare a workflow or pipeline, and you can register each component in the pipeline. For example, in a pipeline, you want to standardize the data first or normalize the data based on the role, okay? And then you do another data preprocessing like PCA to reduce the dimension. And then you do the logistic regression, train the model. But the whole model gonna be the whole pipeline, because when you do the prediction, you need to do the same pipeline, do the same scaling, do the same, PCA reduction, So basically, we want to learn from scikit and build this kind of pipeline idea. So that's why we build transformer as one of the beginning. So it's a way that you can, transformer is an API which can transform from one vector set to another vector set. So we have two API right now over there. One is StandardScaler, which is trying to standardize in terms of the column. And it's really useful like in logistic regression or support vector machine. We are doing that. Support vector machine doesn't work well, actually. And also, it's important for regularization, because we are doing a standardization, you're gonna penalize those those component which has higher variance, right? Because if you don't standardize it, then those component which has higher variance gonna has more important, impact on the whole objective function. So you want to standardize it, and normalizer is normalize it in terms of the row and make it as LN norm. And it's important for some text mining like TF-IDF, this type of work. Okay, so this is API for StandardScaler. So you have a bunch of data point, you parallelize it and make it as a data RDD, and you can do a StandardScaler and pass in, with mean or with standard deviation, and then you can get a model. So it's basically a model contain the mean and variance of the input data, and then you can use it for different data set. And the API for Normalizer is pretty simple. Okay, we also have online summarizer. It's in Spark 1.1. So for online summarizer, you want to compute the mean or variance of the RDD of vector. And you can implement it using naive way. But the naive way gonna have problem, whenever the variance is really small. So sometimes you're gonna get negative variance, and you have better way to do it. So we actually consider that. So you can actually look at the Wikipedia and see how to implement the stable one-pass algorithm to compute the variance. We also optimize it for the sparse vector. So whenever you do the online summarizer on a sparse vector, you don't go through all the elements. But the complexity is all number of the non-zero element in the sparse vector. Okay, so this is the API for summarizer. You can create a summarizer, add in a bunch of vector, and then you can get a mean and variance. Okay, so finally I'm gonna talk about Spark SQL. So Spark SQL allow user to do relational query expressed in SQL or Hive SQL. So it's really useful for lots of business people who can write SQL or quickly write some code to do some prototyping and then do the data cleanup. And schema RDD is basically RDD with type. So each element, each element in the row actually has type. So if you guys are familiar with R, it's kind of like a data frame. You can think about that. Okay, so you can create schema RDD from existing RDD by importing the schema. Or when you load a Pocket file or envelope file, which already have schema, then you can load it directly into schema RDD. So we're gonna talk about how we deal with Spark SQL and MLlib. So with Spark SQL, user can easily load the data from Pocket file or envelope file, which is gonna be significantly smaller than the text file, because Pocket and envelope file is binary format, so you can do compression. And for Pocket, it's actually column storage format, so you can compress it in a column format. And the good thing is that whenever you only pick up a few columns from the data, you don't need to decompress the whole thing. So Pocket is really good in terms of the data storage. It's invented by Twitter and Cloudera. And you can also do Averrow. Averrow is low-based. So in terms of whenever you query it with just a few columns out of a couple hundred columns, then you need to decompress the whole thing and then pick up the column unit. Okay, and MLlib actually considered to use schema RDD as a native input-output format right now. It's kind of like our data frame. So it allows us to create, the output model with the type input, because the model has input and output, right? So you want to know the type. Right now we just use a vector, So whenever you have a categorical variable, you need to convert it into the vector format by yourself. But whenever we have type system built-in, then we can do lots of things automatically, like our data frame. And also, for the schema RDD, we have the column name. And with column name, we can create PMML model much more easily. So this is in our roadmap. So this is one of the examples. Okay, you load the data. First of all, you want to create a schema for the data. So you can create a case class in Scala. So case class is just like a Java class, but you don't need to do new something. Okay, so you have a bunch of variables. And you read the data from the text file, okay? And then you parse it and put it into the case class. So you get a schema RDD, which is RDD of the case class. So whenever you create RDD of case class, it's become a schema RDD. So this is done by implicit conversion inside Scala. Okay, and then you want to create a table, a Hive table inside Spark. So you can do a Regis table as iris dataset. So you cache it. Okay, so basically over here we are actually parsing the text file, load it into schema RDD, and then we register the schema RDD into Hive table. And then we can perform the Hive query. Okay, whenever you do the query, you return another schema RDD. So basically what I did over here is you select the data from the iris dataset where species is equal to stosa or species equal to versicolor. And then you load the data, load the schema RDD, which only has 2 different type of species. And then you can train a binary classifier on top of the data. So this is just one of the examples how people use Hive or SQL combined with MLlib. And it's easy to use it for doing the data preprocessing. And here is the MLlib official guide. And we have GitHub. It's on the GitHub, Apache Spark, so you can download all the source code by yourself. And we have mailing list. So you can sign up the mailing list. Whenever you have question, you just shoot a mail over there, and I'm there all the time. So I can also help you guys to answer the question, and people in the community also can help. Yeah, that's it. So, sure. This one?
Yeah. Excuse me.
Yeah.
Can you make these slides available on your blog?
Yeah, sure. Yeah, I'm gonna put it in SlideShare. Okay. Yeah. Cool. Yeah, that's it. So, any question?
How many of your customers use Java versus the Python?
Oh, Java versus Python? So in our customer, they don't write codes because we provide a web-based solution for them. So they just use the GUI. But I know lots of data scientists use Python. So that's why we try to, in terms of the open source side, we try to push lots of Python binding to the Scala or Java. Yeah, lots of data science use Python actually. Yeah.
You mentioned scikit.
Yeah.
What scale of data do you need to have to make it make sense to start using Spark?
Oh, probably the data bigger than the memory for a single machine. Like, something like 10 gigabyte, I think. Because for a couple gigabyte, scikit gonna be really slow because you don't do parallelization. It's a single thread processing, so it's gonna be really slow. So I think for couple gigabyte, you can still use the Spark in single machine mode because you can parallelize it with multi-thread. Yeah. Cool. So any more question? Okay, great. Yeah, thank you.